Believe it or not, but the speed of light is the worst prison humanity has ever known. Imagine this. We've finally conquered Mars. People live there now. It's fully habitable. You are all excited, sitting in your tiny Mars apartment, which, by the way, you will be paying off for the next 30 generations. But okay, who cares? You take a picture of your new home, proud and smiling, and you send it to your family back on Earth, just to say, look what I bought. You hit send, and you wait 5 minutes, 10 minutes. Then, after 22 full minutes, you finally see red. And right after that, those 3 little dots. I mean, they are typing, for real. 2 minutes, 5 minutes. Oh, you start thinking, oh my god, this is gonna be a big message. 22 more minutes go by, and then it happens. Just a like, that's it. A like. What a shame. From the moment you hit send to that tiny thumbs up, it took 40 minutes. 40 minutes of your life gone forever. And it's not because your family was slow or ignored you. They actually replied right away, as soon as they saw your message. So the question is, what went wrong? The speed of light, that's what. The speed of light is not made of rubber. It doesn't stretch. It's fixed. Always exactly 299,792,458 meters per second, or around 300,000 kilometers per second. And maybe you are thinking, come on, I'm not planning any trips to Mars. Why should I even care? Well, let me show you exactly why. Imagine this. You are an engineer designing a new processor. You've got cutting-edge transistors, a brilliant architecture, but also one huge problem. I mean, modern processors can reach speeds of up to 5 GHz. That means each operation lasts just 0.2 nanoseconds. In that time, a signal, the actual information, can travel about 2.5 inches or 5-6 centimeters. That's the absolute limit. So if any path on the chip is maybe 10 centimeters long, the signal won't make it in time. The whole thing crashes and you have this blue screen. This isn't some sci-fi scenario. It's a real problem in modern microchip design. That's why engineers are now building circuits as short as possible, even stacking them in 3D, just to reduce the distance signals have to travel. Why? Because light can't be cheated. It's not a magical pipe where everything zooms through instantly. It's a boundary. But okay, now let's flip the scene. Imagine you are an investor. High frequency trading. Stock markets, big money. In this world, every millisecond matters. Take the route from New York to Chicago, about 1,200 kilometers. Light takes around 4 milliseconds to travel that distance through a fiber optic cable. Yeah, 4 milliseconds. That's faster than a blink. But in finance, that's an eternity. If your cable is just 10 kilometers longer than your competitors, that adds 30 microseconds of delay. And that's enough to drop your from first in line to second, a difference that could cost millions of dollars. And yes, this is a real problem. In 2010, a company called Spread Networks spent $300 million just to lay the shortest possible fiber optic line between Chicago and New York. Why? To shave off just two milliseconds of delay. And then other companies switched to microwave transmission, because light travels faster through air than through glass. Seriously, hundreds of millions of dollars for a single millisecond, seriously. All to stay ahead in a race against a limit we cannot cross, because light isn't magic, it's a wall. The speed of light, or rather, light itself, is one of the greatest gifts in our universe. But its speed is also our greatest limitation. Shackles we were without even noticing. So here's the real question. Who put those shackles on us, and why? Maybe the world would simply work better if the speed of light were just a little bit faster. Or maybe it would make more sense if it were a little slower. Seriously, where does this number even come from? I mean, 299,792,458 meters per second. Strange. I'm not even talking about the units here. I mean the number itself. Why this speed? Why not faster? Why not slower? Why exactly this value? Is it just a random number that somehow ended up as the speed of light? Well, yes and no, because the same thing applies to other constants in physics. The mass of photon, the charge of the electron, Planck's constant, the gravitational constant, and so on. All of them look completely random, like they came out of nowhere, but they didn't. If you change even one of these numbers, even by a tiny fraction of percent, the entire universe could look completely different, or not exist at all. That number, the speed of light, is more than just how fast light moves. It's one of the key parameters that connects movement through space with movements through time, in a way most people never even consider. Because every object in the universe, you, me, a rock sitting on the ground, even when we seem completely still, we are still moving. And I'm not talking about Earth spinning or orbiting the sun. I'm talking about movement through space-time, or more precisely, through time. Every one of us moves through time at the exact rate of 1 second per second. I know it sounds stupidly simple. Yeah, maybe, but that simple idea came from one man, Albert Einstein. Thanks to Einstein, we know something surprising. Even though the speed of light never changes, the way we move through space-time can. It's not that light speeds up or slows down. No. It's us. We decide how our motion is split between space and time. For example, when you are standing still, all of your movement is through time. You are flowing second by second forward in time. But the moment you start moving in any direction, at any speed, some of that movement shifts into space, and that means less is left for time. The faster you move through space, the slower time slows for you. That's not science fiction. It's the real geometry of the universe. Because your total movement in time and in space always adds up to the same number, and that number is the speed of light. Think of it like this. You have $100 and you need to divide them between two things, time and space. If you spend all $100 on time, 0 goes to space. So you stay still. If you spend, for example, 70 on time and 30 on space, you move a little, and time slows down just a bit. But if you spend the entire $100 on space, you are moving at speed of light, yeah, but time completely stops. Alright, now it gets interesting. If we convert everything to the same kind of units, more precisely to squared units, we enter a whole new world. A world called Minkowski spacetime. Yeah, Polish reference! Minkowski spacetime is like a weird cousin of the space you learned about in school. You know, Euclidean space. The one with Pythagoras and right triangles. But here, time, in Minkowski spacetime, time and space plays different roles. And they are linked together into one thing. In this spacetime, every object, me, you, a slice of pizza or satellite, has a special kind of four-dimensional velocity. Here is the most amazing part. That velocity always has the same value. And the value is, again, the speed of light. Sounds wild, doesn't it? But don't worry. Think of it like a vector. If all your motion goes straight up, you are moving only through time. That means you are standing still in space. If you start moving through space, the vector tilts. Some of it now goes into space, and less remains for time, but the length of the vector stays the same. It's always c, the speed of light. It just gets split differently between time and space. And okay, now think about a photon. That's a whole different story. A photon doesn't spend any of its motion on time. All of its movement goes into space. That's why we say it has zero movement through time. And that's also why its spacetime interval equals zero. Wait. Spacetime interval? What do you mean? Wait for it. How do we even know this? From here. That's the equation. Let's simplify this to just one axis, x. And let's assume the photon moves at speed c. Then you have this. Now we substitute, and after substitution, zero! Not because it's not moving, quite the opposite. It's moving as fast as anything possibly can, but all that motion goes into space and none into time. For a photon, there's no such thing as now. Point A and point B are one and the same event. There's no duration, no present moment, nothing to tick. But here's the strange thing. Light doesn't set that value. The speed of light isn't light's decision. It just so happens that light travels at the maximum speed allowed by the universe. So we ended up naming the constant after it, out of habit. Maybe laziness? Who knows? So if the speed of light is so important, why is it always the same? Why aren't there places in the universe where it's just a bit faster? Or even slightly slower? And here's the twist. There is no known law of physics that strictly forbids that. Nothing says it has to be this way. It's just every time we have ever measured it in every experiment, every setup, every localization, it always comes out the same. Again and again, for centuries. So we just assume it's constant. Like P. Or like the fact that when you drop a cup, it falls down instead of up. If in your home it ever does fall upward, I think I highly recommend calling your local exorcist. Sure, we know light can slow down when it travels through things like glass or water or fog, but that's a completely different story. What we are talking about here in this episode is the speed of light in a vacuum, in absolute emptiness. No particles, no resistance, no interference. So, theoretically, could there be a place far beyond the edge of the observable universe where light behaves differently? Maybe, but we have no way to check. But there's a free game created by MIT Game Lab. At some point, they built a simulator where the speed of light was slowed down to walking speed, like a normal stroll through the park. And finally, you could actually see what happens to space when you are moving at relativistic speed. And it's wild. First thing, as you start walking, your field of view gets wider, literally. Light from the sides starts hitting your eyes at different angles. You see more, even though you are not climbing or flying or just walking. Second, everything in front of you gets brighter. The center becomes more intense because more rays are hitting you head on. It's like the world lights up the faster you go. The third, colors. You get the Doppler effect right in front of your eyes. The image shifts toward violet, then ultraviolet, and eventually X-rays. But only in front of you. Behind you, it's the opposite. It gets darker, shifts to red, and slowly fades away. But the real trip starts later. Space begins to warp. Objects stretch and squeeze, and time starts to slow down. These effects are so crazy. It feels like a psychedelic trip. Don't ask why I know. But without the hallucinations, this is pure relativity. No tricks, just physics. But here's the thing. That game makes you wonder, if all distortions happen at high speeds, then why don't galaxies look warped? Why don't they bend like, for example, oh I know, Captain America's shield in every other Marvel movie. I mean, Logically, shouldn't they? Light has a speed limit. It takes time to reach us, to hit our eyes, telescopes or camera sensors. When you look up at the night sky, you are not seeing the present, we are seeing the past. Those photons have been traveling for years, sometimes thousands, sometimes billions of years. And because of that, the closest alien civilization to us, maybe a few 100 million light years away, might be looking at Earth right now and seeing this. Dinosaurs, not us. But hey, if they are advanced enough to spot dinos, they are probably smart enough to do the math. They know things must have changed. They would guess there's life here, probably even intelligent life most days. But galaxies are a thicker example. They are massive, tens of thousands, sometimes hundreds of thousands of light years across. And if you are looking at one from an angle, the light from the far side has to travel a lot further than the light from the near side. So here's the question: why don't they look warped? Why don't galaxies appear stretched out or twisted like some chaotic smear? Well, the distortion is actually there. It's just so small, we don't even notice it. Sure, you could dive into the hardcore equations here, but skip. Let's keep it simple. If a galaxy is face on, meaning we are looking straight down from the top, then all parts of it are pretty much the same distance away. So no problem, no distortion. But if you are viewing it at an angle, things get sticky. Now, different parts of the galaxy are at different distances, and that means the light takes different amounts of time to reach you. Take our Milky Way, for example. It's about 100,000 light years across. So, if you are looking at it perfectly edge-on, the light from one side would hit you 100,000 years after the light from the other. But luckily, the Milky Way hides itself. It's full of dust. That's why we usually observe spiral galaxies at slight angle, not straight on. And not completely sideways either. Just enough to see the shape, but not enough to mess up the image. And even when we do view them at an angle, remember how slowly galaxies rotate. The stars orbit the center at about 200 or 250 kilometers per second. Our sun takes over 200 million years to make one full orbit. So if there's a 100,000 year delay between the far and near sides, that's just a tiny fraction of a full rotation. The galaxy barely changes in that time. That's why they don't look warped. Yes, there is distortion, but it's so small. We just didn't see it. And when we want to know what a galaxy really looks like, we compare it with others, galaxies that happen to be lined up perfectly, face on or edge on, to give us the clearest possible view. But wait a second, why is the speed of light that specific number? Why not something nice and round, like 300 million meters per second or 4 million meters per second or any other value? Why exactly 299,792,458 meters per second, okay? Well, the answer is surprisingly simple. We don't know. Seriously. There's no deeper law of nature that forces this number to be what it is. It just turned out that way, based on measurements. And over time, we stuck with it. Seriously. Actually, it's the other way around. Since 1983, the meter has been defined using the speed of light, not the other way around. 1 meter is exactly the distance light travels in vacuum in 1 per 299,792,458, etc. of second. So that number 299,792 was literally baked into our measurement system. And yes, the name speed of light can be little misleading, because it's not just about light. That number, c, is the ultimate speed limit of the universe. It's the fastest that any cause can affect any effect. It's the maximum speed at which information can travel. If something happens here and causes a reaction there, that influence can't travel faster than c. But hang on. If you can't go faster than light, what about all those warp drives in science fiction, What about wormholes, space folding, Star Trek, Star Wars? Well, that's where things get interesting. Physics doesn't exactly say no, it says maybe. But it would be really hard, and it would require stuff we don't currently have. Take the Alcubierre drive, for example. It's a real idea, a theoretical concept described by physicist Michael Alcubierre in 1994. And it doesn't move you faster than light through space. No. Instead, it bends space around you. Imagine a sheet of paper. You've got point A on one corner and point B on the opposite. Normally, to go from A to B, you have to travel the full distance. It takes time. But what if you fold the paper? Now A and B are touching and you didn't move faster. You just made the distance shorter. And if the distance is shorter, the time it takes is shorter too, but your speed, it's still the same. That's exactly what a warp drive would do. It would compress space in front of the ship and stretch it behind, creating a weird kind of space-time bubble. From the outside, it would look like faster than light travel, but inside the bubble, nothing breaks the rules, not even light. Sounds amazing, right? Well, there's a catch, actually several. First, such a drive would require negative energy, something physicists call exotic matter. That means a material with negative energy density. No, you can't get that at a gas station or anything else in space. So this is huge problem. But second problem, the amount of exotic energy needed is ridiculous. Early estimates said you would need as much energy as the entire mass of Jupiter, converted into negative energy, by the way. But later models improved on that a bit. But it's still way beyond what we can manage. And last one, third. Even if someone did build such a drive, there's still a problem. Because if something looks like faster than light travel, it might break causality. It could lead to paradoxes, events changing the past, effects happening before the causes, paradox after paradox. If you are interested in that topic about hypothetical drives, space warps, and how we could theoretically reach every corner of the universe, let me know in the comment. Oh, I know. If this video gets 10 likes, I will make a whole episode about it. Quick favor. These videos usually gets 1 like or 2 views. I would love to reach more people, so if you liked this one, maybe share it, send it to a friend, drop it on Reddit. I don't have any English social media, and I can't promote the channel the way I would like to. And if you think one person can't make a difference, you are wrong, because one person can change everything. One share, one comment, that's all it takes to show this matters. To show that it's worth doing, that I'm not alone in this, and someone wants to watch it. And yeah, I know my English isn't perfect, but I'm trying, I'm doing my best. I know I said things a bit funny sometimes, but I didn't want to fake it. I didn't want to use an AI voice, because I can. But it isn't me, this is me. I'm trying, I'm showing up, I'm caring, I'm real. And knowing that someone out there hears me, that means more than I can say. Thank you. Maybe that's enough. Thank you so much. But let's get back to it. Only particles with no mass can move at speed of light, like photons, for example. But in the standard model, they are not the only ones. There are also gluons, the carriers of the strong force. They are massless too, but they never travel alone. They are trapped inside particles like protons and neutrons. That's called confinement. So technically, they are fast, but you will never catch them on the road. And then we've got something like gravitons, theoretical particles that would carry gravity. Nobody's ever seen one, but if they exist, they must be massless too, because gravity also moves at the speed of light. And that's not just a guess. For a long time we couldn't prove it, but in 2017 that changed. Gravitational wave detectors caught the signal from a neutron star collision. And guess what? The gravitational waves and the flash of light hit us at the exact same moment, not even a second of delay, which means, bingo! Gravity travels at the speed of light. So what does that mean? Well, if the sun suddenly disappeared, just hypothetically, for the next 8 minutes, nothing would change. It would still shine in the sky. Earth would still orbit like nothing happened. And then, exactly 8 minutes later, we would get message, I'm gone! I mean, this message. Only then would we feel its absence. But okay, here's the fun fact. There are particles that travel almost at the speed of light, but not quite. Like neutrinos, muchachos, señoritas. They have mass, but so ridiculously tiny, it's almost on the edge of zero. Some theories even include massless neutrinos, but no one's proved that yet. Now check this out. When the 1987 supernova exploded, our detectors picked up neutrinos a few minutes before the light arrived. Sounds like they were faster. We have something faster than the speed of light. No, not really. It's just that neutrinos barely interact with anything. They escaped from deep inside the star instantly, right from the core. But light, it had to wait for the blast to reach the surface. That's why neutrinos won that race. Not because they were faster, but because they didn't get stuck. But here is something that might blow your mind. In particle accelerators like the LHC near Geneva, we speed up protons to nearly speed of light. How close speed of light? The difference between proton and photon? Less than 1/1000%. On a 27-kilometer track, light would beat that proton by a fraction of a millimeter. So this is wild. But no matter how hard we try, we still can't break that final barrier. Why? Because protons have mass. And now, a weird question. How come we know the speed of light so precisely, with no error margin? I mean, every physical quantity has some uncertainty. Well, not this one. The speed of light is special and also a little bit of a trick, because we actually don't know the speed of light in just one direction. Seriously. You would think measuring speed is one of the easiest things ever. You can take an object, let it travel some distance, say 100 meters, measure how long it takes, divide the distance by the time, and boom, you've got the speed. Average speed, sure, in straight line motion, I know, at a constant pace, but still speed! And that's exactly how we measure the speed of light. Seriously. Well, with one tiny but very important catch. Let's picture this experiment. You have a source of light. You send a pulse toward a mirror. It bounces off, comes back, and a detector registers when it returns. A timer measures how long it took from send to receive. If you know the exact distance, you can calculate the speed with amazing precision. And this is how we measure the two-way speed of light. The time it takes to go there and back. And no matter what setup you use, no matter the environment or materials, this round-trip average is always the same. 299,792,458 meters per second. But here's the twist. What if light travels faster in one direction? Like 500,000 kilometers per second on the way out, but slower on the way back, or the other way around. Or what if, and this sounds crazy, it travels instantly in one direction and takes all the time on the way back? Guess what? In every one of those scenarios, your stopwatch still gives the same result, as long as the average speed stays the same. And that's exactly what we are measuring in these experiments. The average round-trip speed. You might think of a clever idea. Instead of using a mirror, just place a detector directly at point B, measure the time it takes light to travel one way from point A to B, and here you are! $1,000,000 to me. This is not the best idea. Here's the catch. You need two perfectly synchronized clocks, one at point A, one at point B. And how do you synchronize two clocks that are far apart. You probably say, maybe I send a synchronization signal from one clock to the other, but that signal can't travel faster than light, which means you need to already know the one-way speed of light to calculate and correct for the delay. Seriously, but that's exactly what we are trying to measure in the first place. The very delay you are trying to fix during synchronization is the delay caused by the one-way speed of light. You might think, okay, let's synchronize both clocks at the same spot first, then we move one of them to its destination. Simple. But the moment you start moving that clock, it's no longer at rest relative to the other one. And according to Einstein's special relativity, moving clocks run slower. So when it finally arrives, it's no longer in sync. But scientists haven't given up. For decades, they've been trying to outsmart this problem, using all kinds of clever setups, sending pulses from the midpoint between two clocks, moving clocks very slowly to reduce time dilation, separating them at constant speeds, even sending light around closed loops. But every single method runs into the same wall. In practice, we always end up measuring a round-trip speed, even if it seems like we are getting a one-way measurement. When you dig into the details, it turns out we are still looking at round-trip result. And that's why physics uses what's called the Einstein conversion. We simply assume that light travels at the same speed in all directions. It's not something we can prove, I know. That's why it's just a convention. But here's the thing, it works. Every experiment we've ever done, from GPS satellites to gravitational wave detectors, relies on that assumption. And the craziest part is that nobody has ever seen it fail. But what if light really doesn't move the same in all directions? What if in one direction it travels just a bit faster, in the other a bit slower? I know it sounds like a pure speculation, maybe, but what if that were true? The consequences would be cosmic, because that would mean there's a preferred direction in space. And if that were the case, the universe shouldn't look the same everywhere. If light moves faster one way than the other, we would expect to see different redshifts in different directions. Galaxies would be disturbed unevenly. One side of the sky might look younger than the other, and most of all, the cosmic microwave background should appear slightly warped. But the thing is, we don't see any of that, at least not at first glance, because the universe on the largest scales seems isotropic. It's the same in every direction. Now, sure, there's a small dipole asymmetry in the background radiation, I know, but we explain that with the motion of the Earth relative to the rest of the universe. Seriously, so we don't need any weird directional differences in the speed of light, okay? So this whole episode, Simon, you mean, so case is closed? Not quite, because there are some theoretical models where relativistic effects like time dilation, length contraction, or distortions in reference frames might actually hide tiny asymmetries in the speed of light. In other words, the universe could have a directional bias, but space-time geometry itself might be masking it from view. And this idea that light might travel faster in one direction than the other hasn't just been left on the chalkboard. It's actually being tested. Seriously. It's tested, and it will be tested through ultra precise systems like GPS, through laser interferometers, and through something called the Sagnac effect. And here is where it gets interesting, because the Sagnac effect seems at first glance, like exactly what we have been looking for. In the Sagnac effect, you split a beam of light, send it in two opposite directions along a closed loop, and when the beam come back, they are slightly out of sync. And it looks like, or sounds like a proof, right? Well, not quite. It's not the light that's speeding up or slowing down. It's the detector that moved. Seriously, the detector is moving. The whole setup is rotating. So one beam has to chase the detector while the other meets it head-on. And voila, that's where the time differences comes from. It's 100% consistent with general relativity. This effect is real. So real that GPS satellites have to account for it. If they didn't, your phone localization, for example, would be off by several kilometers. So do we have proof that light moves identically in all directions? No. But we also have no proof that it doesn't, at least not yet. If you have a way to test it, the comment section is all yours. But back to the main question. Why do we all just assume that the speed of light is the same in both directions? Well, mainly because Einstein said so. In his famous 1905 paper, he just stated it outright. Quote, "We assume the speed of light is the same in all directions." End of quote. I mean, he didn't prove it. He just set it as a rule. And here is the fun part. Even if we don't know whether it's actually true, even if we never find out, special relativity still works. And we use it every single day. GPS, calculating distances to the moon or Mars, planning space missions. All of it is based on that simple two-way speed of light. And it works perfectly. And as I said earlier, countless experiments have confirmed it. But okay, last question. Why exactly is the speed of light what it is? Simple. Because we literally defined the matter that way. Seriously, we could have chosen anything. Feet, miles, even dogs. Anyway, since 1983, a meter isn't a piece of metal or a chunk of Earth's meridian anymore. A meter is defined as the distance light travels in 1/1 of a second. So light didn't get its speed from the meter. The meter got its length from the speed of light. And that's a huge difference, because light speed isn't something we negotiate or agree on. It's a natural constant, unlike the kilogram. Maybe you remember the old kilogram, the one locked in a vault in Sèvres in France, the official chunk of metal that defined mass for the whole world. That thing started losing weight over time. Seriously, this was a huge problem because all measurement system was based on it. But hope arrived in 2019. We changed that. The kilogram no longer depends on a physical object. Now it's defined using Planck's constant, the same constant that helped solve the ultraviolet catastrophe. This strange issue with glowing objects radiating infinite energy. And that Planck constant and Planck equations gave birth to quantum physics, which is a whole new kind of madness, but okay, who cares? So the real question is, how do we measure a kilogram now? We are using something called the Kibble balance, named after Brian Kibble, who invented it. But does it actually work? Well, instead of comparing a mass to physical weight, this device connects mass to electricity and motion. Here's the idea. You've got a coil of wire suspended in a magnetic field. When you run an electric current through it, it creates an electromagnetic force, strong enough to lift the weight or to balance it perfectly. And now here's the cool part. The same coil can also work in reverse. So if you move it through the magnetic field, it generates a voltage. And that voltage can be linked directly to a frequency and to Planck's constant. So in one mode, the balance measures force. In the other, it measures voltage and velocity. And with a few well-known physical laws, we can calculate mass with no physical weights. You don't need it. That's why we now say the kilogram is now tied to Planck's constants. But there are other constants, maybe even deeper ones, the ones that truly govern the universe. For instance, the gravitational constant. This constant controls how strongly mass pulls on the other mass. We have cosmological constant, that weird number making the whole universe expand faster and faster. We have the elementary charge, the mass of proton, the mass of the electron, even the mass of the neutrino, although we are still not exactly sure what it is, but we have something. And then there are the dimensionless constants, like the fine structure constant, which tell us how strongly the electron interacts with the electromagnetic field, or the number of spatial dimensions. Yeah, that's a constant too. In total, we've got something like 26 or 30 fundamental numbers. They are just built into our physics. Each one has a very, very specific value, not derived from any deeper principle, at least not from anything we know today. But here is even the weirdest part. These numbers look totally random, like someone rolled dice, but they all work perfectly. And what's worse, if you changed even one of them by the teeniest fraction, the entire universe might collapse or not even exist at all. Let's take just one simple example from nuclear physics. Inside every star there is a crucial reaction. Two protons collide and forms a deuterium nucleus. That's a hydrogen isotope, a proton and a neutron. But hold on, they don't just snap together like Lego bricks. One of those protons has to turn into a neutron. And when it happens, it releases a positron, the positively charged version of an electron, and an electron neutrino, a tiny, nearly massless particle. That's the first step in the chain reaction we call nuclear fusion. But here's the catch. If you increased Planck's constant by just 15%, the deuterium nucleus would become unstable. It will fall apart before doing anything. No reaction. And if the reaction doesn't happen, stars don't ignite at all. And even for this to work at all, the universe had to cheat a little. See, protons are both positively charged, and like charges repel, to get close enough to fuse, they need to overcome the Coulomb's barrier, the electrostatic repulsion between them. And guess what? Even at 10 million Kelvin, their energy isn't enough. So enter quantum tunneling, a cosmic cheat code for protons. Instead of blasting through the barrier, the proton just show up on their other side. No explosion, no impact. It just appears, not by magic, by probability. Quantum mechanics doesn't say these photons will fuse or not. It says there's a tiny chance they might. And if you have trillions upon trillions of protons, and you do, then eventually one of them will. We don't know how, we just know it happens. And that's enough. This is how fusion in stars begins. Protons tunnel through their mutual repulsion and bind together. But without quantum tunneling, there would be no fusion. Not even in the hottest cores of stars. But this whole setup only works because of balance. Delicate, fragile balance. Change Planck's constant even by 15%, and the probability of tunneling drops. Deuterium falls apart. Fusion doesn't happen. Stars never ignite. And what do we get? No light, no heat, no stars, just cold, darkness and disappointments. One of the key players here is the weak nuclear force. That's what controls the speed of fusion reactions in stars. If it were stronger, stars would burn their fuel too fast. They would burn out before planets could even form. If it were weaker, some stars might not go supernova at all. And without supernova, there would be no way to spread elements heavier than iron. Which means no rocky planets, no life, no us, literally, no building blocks for the universe. And that's just the beginning. Even the mass of the proton is critical. If it were just 0.1% smaller, protons would spontaneously decay into neutrons, positrons, and neutrinos. And suddenly, boom, no matter, just a chaotic plasma soup with positrons and electrons constantly annihilating each other. And the result? No light, but a deadly storm of gamma radiation, a radioactive nightmare. And then there's carbon, the element we are all made of. It doesn't just happen. In large amounts, carbon forms through something called the Hoyle state, an excitement configuration of carbon-12 nuclei. But this state is extremely sensitive. If its energy were just 2% higher or lower, carbon production in stars would drop to nearly zero. And with no carbon, there is no cells, no DNA, no biochemistry, no life. And what about electron? Sounds like a small thing, but its mass matters. Right now, the electron is about 1,836 times lighter than a proton, and so on. If the ratio were different, even slightly, the size of atomic orbits would shift, which means chemistry stops working. No molecules, no bonds, no matter. At least, not the kind we know. No chemistry, no life. And now we move higher, into cosmology. Even the average density of matter in the universe had to be just right. If it were even a tiny bit higher than the so-called critical density, the universe would have had a positive curvature, collapsed on itself, and ended before anything could form. Like balloon, collapse. Expansion would have been too fast. Matter would have spread too thin. No galaxy, no stars. But here's what we actually observe. The density of the universe is within 1 part in 100,000 of the critical value. 1 decimal place in every 100,000. That means the universe isn't closed, isn't open. It's perfectly flat, like Earth. No. Earth is round. All of this. Every bizarre coincidence, every fine balance, every strange ratio, it has a name. All of this strange situation has a name, fine tuning. The idea that the universe looked like it was carefully calibrated, tuned to precision. Yes, we will have to throw cosmic inflation into this mix too, but we will get there in a moment, okay? Let me introduce something first. The term fine tuning was first introduced in the 1970s, and over time it's only gained more attention. Because the more we discover, the stranger it gets. Every new constant, every new experiment just adds another piece to this razor-thin puzzle. So the real question is, did we just get cosmically lucky? Did we roll the perfect dice and boom, here we are? Or maybe this isn't luck at all. Maybe there is something deeper behind it. And that's where the hypotheses begin. Each one different, each one fascinating. Let's keep going. The first theory, honestly, it's kind of boring. It says all this fine tuning is just an illusion. Why? Because we simply haven't discovered the so-called theory of everything yet. I mean, some universal rule that would make all the constants in physics fall into place naturally. No manual input, no tweaking, no magic numbers. Imagine it. Like, you've got 30 random values scribbled on a piece of paper, and then someone show you one beautiful equation that explains every single one of them. Elegant, precise, clean, right? One of the candidates for such a theory is string theory, which claims that every particle is usually a vibrating string of energy. Sounds awesome, right? Well, there's a catch. For the theory to work, you don't just need 3 spatial dimensions. You need 10, but we only see 3. So what happened to the rest? According to the theory, those extra dimensions are curled up. So tiny, they are hidden from our view, that's all. And that's where something wild comes in. Physicists call it the string landscape. Each way of curling those dimensions produces a different universe, different particles, different forces, different laws of physics. There could be as many as 10 to the power of 100 possible versions. Seriously, that's huge. That's 1 and 100 zeros. That's more than the number of atoms in our observable universe. But here's the other problem. We have no clue which version of universe is ours, or why we got this one. So for now, we are still in the dark. But now it's time for the second theory. Way more controversial, but kind of intuitive. What if this universe was designed? This isn't about some God sketching our planet orbits or a golden score. All by the way, okay. Religion topics. Bye. I mean, maybe someone, a mind, a program, an entity, set the initial conditions typed in the physics, hit start and walked away. A simulation, a perfect clockwork universe running on its own. No divine micromanagement, just code. But it brings question, was it God? Was it programmer from a higher reality? Or maybe us from the future? We don't know, and that's the problem. Because then you get stuck in the endless loop. Who created the creator? And who created that one? It's unprovable, a scientific dead end. But still, imagine a cosmic supermind tuning 30 universal constant with laser precision, setting the rules of reality just right for life to emerge. And YouTube. Yeah, YouTube is the best. Yeah, I love YouTube. Or maybe our universe isn't special at all. Maybe it's not even unique. Maybe there's an infinite number of other universes, each with different laws of physics, different constants, different particles in one. For example, gravity is maybe stronger, 100 times stronger. In another, photons weigh a ton. In yet another, there's no light at all, because the speed of light is 3 centimeters per second. I mean 1 inches per second, okay? For Americans. Or space feels like jelly, the full reality menu. Each of these worlds is sometimes called a pocket universe, and the full collection of them is called multiverse. Sounds like Marvel, sure, but in physics it's no joke. Where does the idea come from? Well, according to one hypothesis, our Big Bang wasn't special. It wasn't a global explosion of everything, but more like a local pop, a tiny spark in one corner or something much bigger. In more technical terms, it's called eternal inflation. I told you we would get to that. It's the theory that the space is always expanding, but not evenly. There are quantum fluctuations, and where inflation randomly slows down, a separate bubble forms, a brand new independent pocket of reality. Imagine a giant cosmic bubble, the largest one you can think of. It's expanding in every direction all the time, but not at the same rate everywhere. In some spots, that expansion suddenly slows down, like a glitch in the Matrix. When that happens, something crazy occurred. A smaller bubble breaks off of the big one, then another and another. Each of them is a brand new universe, with its own laws, fundamental constants. One has stronger gravity, one has more dimensions, one might not have light at all, and ours just one of those bubbles, randomly tuned just right for life. And the whole thing, that giant field still bubbling and branching and expanding, that's the multiverse. And here's the kicker. Some of those universes might form close enough to each other to actually collide. Some scientists actually believe that a cosmic collision like that might have left a mark. Where? In the cosmic microwave background, that ancient glow from the childhood of the universe. If one of those bubbles crashed into ours, it might have left a signature, a bruise on the sky, might a cold spot, might a ripple pattern. Sounds exciting, right? Sure, but here comes the cold shower. So far, nothing confirmed. We have seen a few weird things, some anomalies, some inconsistencies in the satellite data from Planck and VMAP, but it could all be just noise. Maybe something is there, maybe not. But there is another idea, one that, at least in theory, could actually be tested. It's called cosmological natural selection, and it was proposed by physics Lee Smolin. Imagine Darwin's theory, but not for living things, for universes. According to this concept, every universe might have offspring, and the birthplace of those baby universes? Black holes. Yeah, those same black holes that devour light, matter, time, and hope. Deep inside, where physics breaks down, something new might begin. A reset, a new space-time, a new Big Bang, a brand new universe. And here's the craziest part. The parent universe might pass on some its traits to its children. Not all of them, just enough, with tiny random differences, mutations, just like evolution. This creates a kind of cosmic natural selection. But here, it's not about who has the best clothes or fluffiest tail. It's about who makes the most black holes. The more black holes a universe produces, the more kids it spawns. And those kids slightly different. They make more black holes and thus make more universes, and on and on and on. And now comes the twist. The same conditions that favor black holes also favor life. You need 3 spatial dimensions. You need long-living stars. You need carbon, you need time, and suddenly that's exactly what we've got. So what's the conclusion? Maybe we are not the center of the universe, maybe we are just a side effect, a product of a black hole Darwinism. And the best part? This theory doesn't rely on any divine force. It doesn't claim someone planned anything. It doesn't say that the universe was made for us. It doesn't even depend on the anthropic principle. It is what it is because otherwise we wouldn't be here to notice. No, here everything unfolds naturally, ordinary, without design. Sure, we have no proof it's true, but we also have no proof it's wrong, and that is something. But think about it. If every universe is born from a black hole in another, then who made the first black hole? Or maybe there was no first. Maybe this process has always existed. Or maybe someone somewhere hit start. Well, there's another explanation for all this fine-tuning. Maybe not as thrilling, but definitely grounded. Maybe the whole thing is just an illusion, a result of how we are looking at it. Because what do? We take a single physical constant, we tweak it just a tiny bit, and boom, the universe collapses. Okay, but that's not really fair, is it? Who says you can only change one thing at a time? What if we tweak 2 constants, or 3, or 10? What if their effects cancel each other out? Maybe something that breaks the universe in one scenario actually saves it in another. Take stars, for example. Their entire behavior depends mostly on 4 values. The proton mass, the electron mass, the strength of the electromagnetic force, and the strength of the strong nuclear force. So American physicist Victor Stengen had an idea. What if we treat those values like sliders in a simulation? He built a basic model and called it the Monkey God Simulator. Why Monkey God? Because it was based on a twist of the old Shakespearean monkey paradox. Maybe you know it. If you sit a monkey in front of a typewriter and give it infinite time, eventually it will type out the complete works of Shakespeare, randomly, without thought, but it will happen. Stenger tested what happens when you randomly set those 4 sliders. And guess what? You don't have to land on our exact combination to get a working universe. In many of those simulations, stars will formed, fusion will worked, atoms existed, time passed, planets orbit. Some of those worlds would be very strange by our standards, but they had stability. They had structure, they had the time needed for complex systems to evolve. In other words, maybe we don't live in the only possible world. Maybe we are just one of many combinations. One that works well for us. Maybe this whole fine-tuning idea is just an illusion. Maybe all those constants, charts, and symmetries are just a side effect of how we look at things. Because our brains love to see patterns, even in chaos. Maybe the universe doesn't have to be perfect to work. Maybe some constants could change by 10%, 20%, and reality would still hold together. Slightly weirder, a bit different, but still with stars. Maybe even still with us. Maybe we are just one of many versions that simply worked. We just don't know yet. Maybe we won't for a long time, but that's the beauty of it. Yeah, I know it's long, but I love episodes like this. They are not just physics. They are philosophical deep dives into the fabric of reality. Next week, we might discover something that flips it all upside down, because the universe isn't a story with a happy end. It's not a book with a final chapter. Universe, it's a journey, ongoing, endless, toward something. What exactly? I will be totally honest with you. I don't know. And maybe the goal doesn't matter that much. Maybe the journey itself is the goal. But I know one thing. Every question we have answered. Every question we are answering. And every question we will answer will always lead to 3 or 4 or 5 new ones. But the important part is that we never stop asking. Why? Because that is what makes us human. Bye. See you in the comment section.